Hello, welcome to this last video on P2 AQA GCSE Physics. We're just going to look at atomic structure because the whole video is about radioactivity and it's important we review atomic structure before moving on. So first thing, protons and neutrons are found in the nucleus of the atom, and a proton has a mass of 1 and a neutron has a mass of 1. Electrons, however, are found in shells around the outside of the atom and they have a mass of 0. In terms of charge, electrons have a negative charge, protons have a positive charge, neutrons have a neutral charge. Now, every element in the periodic table is named based on its number of protons. So carbon has a certain number of protons and that's what makes it carbon. Hydrogen has a completely different number of protons and that's what makes that hydrogen. Now, an isotope has the same number of protons as any other atom of that element. So for example, all the isotopes of carbon all have the same number of protons. However, what's different about an isotope is an atom that has a different number of neutrons. So you can have loads of different atoms that are all the same element because they've all got the same number of protons, but because they've got different neutrons, they're called an isotope. So if you look at the atomic numbers of these isotopes, they're all the same, but if you look at the mass numbers, they're all different. Because radioactive isotopes are isotopes that want to break down. Now, when their nuclei decay or break down, they release radiation, and this radiation can be in three forms: alpha, beta, and gamma radiation. Now, radiation is around us all the time. If I set up a Geiger counter now, right next to me while I'm making this video, you'd hear clicks, and each click would represent a nuclei decaying. Because just around you, everywhere you are, there is some radiation. Some of it's left over from the Big Bang, some of it is being emitted from radioactive materials like rocks, or cosmic rays from space, or even trace amounts from when we've used nuclear weapons in the past, or there have been accidents in nuclear power plants. At low levels, background radiation is not a problem. It's fine. However, if you were to set up a Geiger counter next to somewhere where there'd been a major accident, the amount of clicks going off would be through the roof, and this would be a real big problem because if you have high levels of radiation, it can lead to death, it can lead to mutations, and it can lead to things like cancers. And this can be long-term as well. So there are some areas where nuclear weapons have been set off, or where nuclear power plants have exploded for whatever reason, that are now completely abandoned, and you can't go there because it's too risky, because this radiation is really, really high level. So the three types of radiation you need to know about are alpha, beta and gamma. Alpha radiation is made up of 2 neutrons and 2 protons. And in air it can only travel about 5 centimetres. This is because it's the largest type of radiation. It can also be stopped by paper, which is kind of handy. So it doesn't travel very far, and it certainly can't travel through anything thicker than paper. Saying this though, it's still harmful. Alpha radiation is actually the most ionising form of radiation, which means it's capable of knocking electrons off other atoms really easily, and because it's most ionising, it can mutate DNA and it can lead to cancers quite easily. Luckily though, most of the time we can't get alpha into somebody's system because obviously it can't go through paper, so there's no way it can get through skin. But if you were to ingest alpha, it would be the most harmful. Now, beta is made up of a single electron, and in air it can travel a bit further because it's a bit smaller than alpha, so it can travel up to 1 metre in distance. It can also travel right the way through paper, but aluminium stops it, so a thin sheet of aluminium stops beta radiation. Beta is a little less ionising than alpha, but it's still more ionising than gamma. Now finally we come on to gamma radiation. Gamma radiation is made up of an electromagnetic wave. Now because it's a wave, it can move through air an unlimited amount of distance. It just can carry on going. The only thing that seems to stop it is lead. So if you ever look at radioactive sources in school, they've probably been brought out to you in a lead-lined box. And this is because lead stops everything, even gamma radiation, from passing through it. Now, the final thing you need to know is alpha and beta radiation can both be deflected by electric and magnetic fields. Gamma cannot, because it's just a wave. You also need to be aware that alpha, because it's slightly larger, isn't deflected as much as beta. So deflected means moved off course. And also it deflects in the opposite direction. So now we look at radioactive decay and balancing radioactive decay equations. This is a higher tier skill, so don't worry about it if you're on the foundation paper. So over this side of the equation we have the radioactive isotope that's going to be broken down, and you can see it's got 90 protons and it's got a mass number of 228. Now if you didn't know these numbers, you could look them up using the periodic table. Now remember, the mass number is the number of protons plus the number of neutrons. Now over the other side here we've got an alpha particle being released, and we've got the element that's being produced from this decay. So an alpha particle, remember, has got 2 protons. So first of all, I can fill in the proton number of the alpha particle of 2, and it's got a mass number of 4 because it's got 2 protons and 2 neutrons. Now by knowing these two numbers, we can work out what these are, because this original element here is the only thing that's being broken down to release this alpha. So all we need to do is do 90 minus 2 for the number of protons, and we're going to get 88 protons. And then for the mass number, we're just going to do 228 minus 4. So we're going to get 224, and that's that balanced equation. Now you might also be asked to balance an equation where a beta particle is given out as radiation. So here again we've got a radioactive isotope that's going to be broken down. This time it's got protons, number of 19, and it's got 40 as its mass number. Now beta particles are always written in the same way. So a beta particle always has a mass number of 0 and always has a proton number of minus 1 because it's got that minus charge. Now we know this doesn't have a proton. The beta particle isn't made up of a proton, but this negative 1 symbolises the fact that it's an electron. Now we're going to look at what element is going to be made from this decay. So we can start off by looking at this number here, the mass number, the top number. Now beta decay is always released when a neutron changes to a proton plus an electron, and this electron is then given out as the beta decay. So the top number, the mass number, should remain unchanged, because all you're doing is switching a neutron, which has a mass of 1, for a proton, which has a mass of 1, and then releasing your electron, which doesn't weigh anything in the first place. So your mass number remains the same at 40. The number that does change in this case is your atomic number, because you're switching a neutron for a proton. So now you just need to add a 1 onto your atomic number, and that gives you the number of protons that your new element has. So we'll just check this. My numbers will come up underneath, as confusing as that is. And you can see, yes, we're all spot on. Scientists commonly talk about the half-life of radioactive elements. What they mean by half-life is the amount of time taken for half the sample's nuclei to decay or to break down. Now on a graph, this looks like this. There's a downwards curve to it. So if we start off with 100% of our sample, by the time we've had 1 half-life, that 100% of the sample has decreased to 50%. If we have 2 half-lives, the sample will have been decreased to 25%, and so on and so forth. Now, the way that we can tell what percentage of the sample you've got is by using a Geiger counter. Now, a Geiger counter clicks every time it hears an atomic nuclei decay, and this is known as the count rate. So the time it takes for the count rate to drop by half is known as a half-life. So common questions include things like this, where they ask you, well, the half-life of an element is 2 days. How long would it take for the count rate of that element to drop from 320, let's put a count rate, to 20? So what you need to do is you first need to work out how many half-lives this must have gone through in order to go from 320 as your count rate to 20. So what you'll do is you'll write 320 and then a little arrow and halve it. So I've got 120 60. Then, if I halve it again, I'll get 80. If I halve that again, I get 40. And eventually, if I halve it again, I get 20. So this tells me how many half-lives my element has been through to go from a count rate of 320 to 20. And it must have been through 1, 2, 3, 4 half-lives. Now, I was told in the question, each half-life is worth 2 days, or as long as 2 days. So I'm going to do 4 times 2, which tells me it would take 8 days for my sample with a half-life of 2 days to drop from a 320 count rate. The last thing that's covered in P2 is nuclear fission and nuclear fusion. So nuclear fission is the splitting of an atomic nuclei. And this is something that humans have been able to harness, and we use it in nuclear power stations. And it's really, really effective at creating huge amounts of energy. So the two things that we commonly use in nuclear reactors are uranium-235 and plutonium-239. But to start a reaction with either of these two atomic nuclei, the first need to absorb a neutron. So this starts off fission, this neutron. And when fission starts, the neutrons created then start a chain reaction. So if we look at this example here, we've got uranium-235 here, and it's being hit by a neutron. Now when that neutron hits that uranium, the uranium breaks down and it releases 2 other atomic nuclei and 2 more neutrons. Now these neutrons are important because there's more uranium in that reactor ready to be reacted with, and those 2 neutrons each go on to hit another uranium. When that uranium is hit, it releases 2 other atomic nuclei and then 2 more neutrons. And each of these neutrons goes on to hit another uranium, and so on and so forth. So you can see that from this one uranium atom and this one neutron, a massive chain reaction can occur that escalates and gets bigger and bigger and bigger and creates more and more energy, because each time these neutrons hit another uranium and the uranium absorbs a neutron, the breakdown that happens afterwards releases large amounts of energy. Now, the one thing you need to be aware of is they can lower control rods into this tank, and these control rods can be used to absorb extra neutrons. So if your reaction is going a bit too wild and there's a bit too many neutrons available for these chain reactions, and they want to slow down the chain reactions, they can lower the control rods into the reactor, and so some neutrons, extra neutrons, can be absorbed into the control rods. Equally, if you want to speed up your reaction, you want to create more energy, you lift out the control rods and just let the reaction go. So it creates huge amounts of energy. It's a chain reaction, and it occurs when neutrons are absorbed by uranium. So nuclear fission is where atomic nuclei break down, but nuclear fusion is where they join. And nuclear fusion happens when you get 2 atomic nuclei joining to form one larger one. It happens in all stars, and it releases huge amounts of energy. So our star right now has the fuel source hydrogen. Hydrogen is continually being fused to create helium. Now, for the back end of P2, you need to know about the life cycle of a star. So, life cycle of a star starts with a protostar, and this is a ball of dust and gas that's pulled together by gravity. Now, if the force of gravity is strong enough, it will start fusion, and the gases inside the protostar will start to fuse. And this will form a main sequence star. Now, a main sequence star is usually stable, and it maintains kind of a balanced shape because all the forces acting in it are balanced. So the pressure and the temperature created by this huge amount of fusion is balanced by the gravity pulling it in on itself. Now, during this fusion, all the elements we know on Earth are created, and if there's ever a massive explosion and this star explodes, so a supernova, this is when these elements can be spread out in a universe. During the stable period of stars, the fusion can create elements up to and including iron. So anything not as heavy as iron can be created. However, elements heavier than iron can only be formed when supernovas occur. And supernovas are giant explosions. So this is one piece of evidence for the Big Bang, because we've got all these elements on Earth that are heavier than iron, but they can only ever be formed if there was a supernova, if there was a giant explosion. So to have these on our planet you would assume this means that there must have been a giant explosion to create and fling these elements far out into the universe. So now, after you've had a main sequence star, the star could take one of two paths, and it depends on the size of the star. So if you have a star that is about the same size as our sun, then once its fuel source starts to run out, its hydrogen, it starts to expand a little bit, and it starts to become a red giant. After a red giant, when its fuel source is really kind of running low, it eventually starts to contract in on itself, and gravity pulls it inwards, and then it forms a white dwarf. Now, when this white dwarf cools even further, it then forms a black dwarf. Now, if you've got a main sequence star that's much bigger than the sun, this is where quite interesting things happen. So your main sequence star will balloon outwards, it'll get much bigger, and it'll become a red supergiant. And at this point, it'll get much hotter, and eventually it'll explode, and it's a massive explosion is called a supernova. Now, at the end of a supernova, one of two things can form. Either you could form a neutron star, which is really, 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 really dense star that would then cool, or you could form a black hole. And a black hole is an area in space where nothing can escape it. So it's got huge amounts of gravity, and it pulls things inwards on itself, and even like light can't escape a black hole. So it's dead interesting. And if you've got time after your exams, go and research it. So good luck with P2. That's everything you need to know.